Jai Hind to all of you. I am Dr. Ritish Kumar. I am going to present this lecture on the topic of bipolar junction transistor, that is also known as BJT, and base width modulation. So let's begin with the topic. So this is a university syllabus which is categorized or which is divided into 5 units. So this topic lies in the unit number 4. As you can see here, bipolar junction transistor. Unit number 4, bipolar junction transistor. So I will be covering this topic in this lecture. Next, the recommended books. So first two books are very important books. So I will prefer these two books for the reading of this topic. So this is the first book is Benjamin's Treatment, and second book in Neiman and Donald. These two books are very good books. So let's begin the topic BJT, bipolar junction transistor, and different operating region. So as we know, there are two kinds of junction transistor. The first one is the NPN and PNP. Right. So first we need to understand why we call the bipolar junction. Bipolar junction. So it has two junctions. The first one is the ammeter base junction, junction in between ammeter base, and junction in between collector and base. So it has two junctions. The first one is ammeter base junction, and the second junction is a collector base junction. And why we call the bipolar also because the flow of the current or the conduction process happening due to the presence of both charge carrier, that is minority carrier, majority carrier. So there is a concept there is some concept of regarding the reverse bias reverse saturation current that will be covering in the next slides. So first we need to understand what is a PNP and NPN and different types of different operating region. So because it has two junction, ammeter base junction and collector base junction, so we have a four combination four combination for the different biasing cases for these two junction. So you can see here, this is a PNP transistor and this is a NPN transistor we have taken here. So you can see here, this is a ammeter, this is a base, this is a collector. Again, here in the case of NPN also, it has ammeter, base, collector. So there is a junction in between ammeter base junction. This is represented by JE, and this is a junction in between base and collector. That's why we call collector base junction, and it is represented by JB. So ammeter is represented by E, collector is represented by C, and base is represented by B. Similarly, we have in the case of NPN transistor, this is a ammeter, this is a base, this is a collector, and this is a junction of in between ammeter to base, and in between collector to base is represented by JC. So we have a different four combination for different biasing of these two junctions. That's why we have a four different operating region. So as we know, we have for a diode case, we have two different kind of biasing. The first one is forward bias and second one is a reverse bias. So in the case of forward bias, we need to connect the P with positive and N is connected with the negative terminal of the battery, while in the case of reverse bias, P is connected with negative and N is connected with the positive of the battery. Right. Similarly, we need to connect for this junction and this junction in the forward case and reverse bias case. Right. And this is a representation of symbolic representation of NPN transistor and PNP transistor here. So you can see this arrow is representing the flow of direction of current. Right. In other words, the arrow always represented the ammeter terminal. So this is ammeter terminal, this is ammeter terminal, and direction flow of current is in this direction. So this is a NPN transistor, this is a PNP transistor. Also arrow direction is represented N type, NPN. So this is again P and P, right? So this is a symbolic representation of these two transistors. So we have four different operating regions. The first one is a cutoff region, active region, saturation region, reverse active region. So for the cutoff region, the both junctions should be in the forward bias, in the reverse bias. This is a reverse bias. We need to connect these two junction with the in the form of reverse bias case. Then the transistor function will be acting as a switch in off condition. It will act as a switch in off condition, right? Similarly, if you see a different case for active region, the ammeter base junction, that is represented by J as well, and this one is JC. So J is in the forward bias and JC is in the reverse bias. So the transistor will be in the active region and it will act as an amplifier, right? And in the third case, in the saturation operating region, the first junction, that is ammeter base junction, should be in the forward bias, and collector base junction should be in the forward bias. Both junctions should be in the forward bias. Then it will act as a switch in on condition, right? Act as a switch in the on condition. And the last one, and the fourth one, is the reverse active region, in which you have to connect the ammeter base junction in the reverse bias while the collector base junction is in the forward bias. Then we have a reverse active region, because in active region BJT act as an amplifier. So in the reverse active region it will act as an attenuator or inverse of amplification, that is also known as attenuator. So in the reverse active region, transistor will act as an attenuator. So these are the different application of transistor for different operating region. So transistor can be act as a switch, act as an amplifier, or act as an attenuator as well. So these are the different operating regions we need to understand to identify the application of the bipolar junction transistor. These are this table specify the different operating region and application, doping level. Here these all are the first four section 1, 2, 3, 4 already we have studied in the last slide, but the fifth one column is a doping level we need to understand. So in the last slide we can see here, this is ammeter base collector. So in the figure you can have what kind of doping we need to have in the case of ammeter, base and collector. So ammeter, here the ammeter is a moderately doped, and base is a lightly doped, and collector is the ammeter is a highly doped, and base is a lightly doped, and collector is a moderately doped. So in the table we have mentioned it, ammeter is a heavily doped, and base is a lightly doped, and collector is the moderately doped. In all the cases we need to have a same kind of doping level in the BJT we have. So this is a total explanation of the BJT, either in terms of different operating region and doping level. Next, we need to understand what kind of size of ammeter has, base has, and collector has. So this is a table specifies the size, physical size of the ammeter based collector, doping level, concentration, as I already studied in the last slide. So you can see here ammeter is a moderately moderate in size, and base is a very thin in size, and the collector is the widest region, that is the largest size uh, in all the emitter, base and collector. So if I say in a single line, in the case of doping profile, if I write doping profile, so doping profile in the case of emitter is highly doped, base is a lightly doped, and collector is the moderately doped. So base is a lightly doped, emitter is a heavily doped. In terms of if I write in terms of means in terms of physical size profile, the order of physical size profile will be collector is the largest in size, then emitter, then base is the narrowest one. So this is the largest one, this is the smallest one. Base is the smallest in the area and collector is the largest in area. So we need to understand the profile irrespective of doping and irrespective of physical size. So next is a this is a diagrammatically representation of NPN and PNP, and this is a in the circuit form we need to make it like in this fashion. So you can see here, this is emitter, base, collector. So in between emitter and base we have a representation of voltage like BEB. This is a voltage in between emitter to base. This is a voltage in between collector to base, right? That's why we write in the fashion of CB and in the fashion of EB, right? So this is PNP type transistor, because arrow is representing inside, and if arrow is representing outside, this is NPN transistor. And again this is a emitter base voltage, this is a collector base voltage, right? And this is the direction of emitter current, base current and collector current. So this is a representation of symbolic, and either diametrically we have a representation like in this fashion. Next is this is a potential profile and minority carrier concentration profile of open circuited transistor. So you can see here, this is an ideal case. If I plot the potential of the ideal case PNP transistor, here we have taken PNP transistor, right? So this is a junction of this is a emitter junction, this is the collector junction, because there is discontinuity in between emitter to base and base to emitter. So we have a contact potential in between this junction. This is a PN junction. Similarly, as we have in the diode, so this is a contact potential of emitter base junction. This is a contact potential in between collector base junction. So this profile is looking like in this fashion. This is a contact potential of PNP transistor, right? If I talk about the minority carrier concentration, so this here we are talking about the minority carrier. So we need to plot the concentration diagram for minority. So if I talk, this is P and P. So in the P we have a electron as a minority carrier. In the N we have a hole as a minority carrier, and the P we have a electron, again electron has a minority carrier. So this is a concentration profile of electron. That's why we have represented here with N, right? So this is NPO. This is representing the electron concentration P type semiconductor. So this is a profile, concentration profile of electron, and this is a concentration profile of hole. So because this is a heavily doped, that's why the minority carrier concentration is low as compared to the base, because base is a lightly doped. So base has a more minority carrier concentration as compared to the emitter and collector. That's why this concentration is higher. This concentration is drawn over the above the this concentration level. That's represent the base is a lightly doped, or base has a more minority carrier concentration is respected to emitter and collector. So this is a representation of minority carrier concentration again, and this is this configuration shows the transistor is in active region. Why? Because this junction is connected in the forward bias. You can you can see here, this is a PNP transistor, PNB. P is connected with positive, N is connected with negative. So this junction is in the forward bias, and this junction is in the reverse bias. That's why this transistor will be acting as a active region, will be acting as an amplifier as well. So we need to understand what will be the effect on the contact potential if we connected the transistor in this fashion, that is in the active region. So you can see here, this is in the forward bias. This junction is in the forward bias, and this junction is the reverse bias. As we already know, if in the PN junction, right? If in the PN junction, the junction is connected in the forward bias, then the contact potential or contact barrier height will be reduced by the amount of the forward bias voltage. Similarly, if we connected the junction in the reverse bias, then the depletion layer we say, contact potential height or contact potential barrier height will be getting increased by the amount of reverse bias voltage. Similarly, we have in the case of emitter junction. So previously this dotted line is representing the unbiased case, right? Dotted line is representing the unbiased case. In both cases, the contact potential has the same amount, that is represented by V naught. So if emitter base junction is connected in the forward bias, then this contact potential or barrier height is reduced by the amount of forward bias voltage, that is BEV. That is, this is this forward bias voltage is BEV, right? So this contact potential is reduced by the amount of BEV. Similarly, if we look at the collector base junction, so in the collector base junction, this is in the reverse bias. So this contact potential barrier height is increased by the amount of reverse bias voltage here. So this barrier height is decreased, and this barrier height or contact potential is increased by the amount of reverse bias voltage. So this is a representation of contact potential height for this this BJT is in the active region. So we need to understand this contact potential, because we need to understand how the carrier charge flow from emitter to collector, right? So next topic is the concentration level diagram. This is a minority carrier concentration diagram. So as we know, the concentration, the charge carrier always flow from the higher concentration to lower concentration, and the concentration or concentration decrease with respect to distance exponentially. So here we have drawn exponential decrement in the concentration level. So here I am talking about the PNP transistor. This is a PNP transistor, right? So in the P, the minority carriers is electrons. In the N, the minority carriers are holes. Again in the P, minority carriers are electrons. So here you can see here, previously the dotted line is representing the case, then where we have unbiased case of the transistor. So this is a unbiased case. Dotted line is representing the unbiased transistor, right? So when we talk about the active region, this junction is in the forward bias and this junction is in the reverse bias. So in the forward bias, you have to connect this p type terminal with positive and n type terminal with negative. So hole is mean the electron is moving from I mean hole is moving from p to n and electrons will be moving from n to p, right. So here at the junction terminal or at the junction point, the concentration level of concentration of level of holes will be increased. Previously unbiased it has the concentration level at this point. When the you have if you connect this junction in the forward wire, the hole is transferring from p to n. That's why the at the junction point the concentration level is very high, and as far as you move towards the collector, if the distance is increased, the concentration level will be decreased exponentially towards the collector sides, right. So if I talk about this concentration, because holes are moving this is connected to positive, so electrons are moving from uh, moving from N to P. That's why at the junction point the concentration of electrons will be high as compared to the previous unbiased case. So and it will decrease again in exponentially form towards the towards the towards if you increase the distance, right. So now if I talk about this junction, so uh, here the mean the holes are moving from uh, mean N to P. So some electrons and at this junction the recombination will be happening at this junction. Uh, that's why this junction at this junction the concentration level for the minority carrier is low, and if you move towards the if you increase the distance and moving higher distance, the concentration level will be high. So here you are here this at this terminal why we taking the concentration is low, because at this junction recombination will be happening in between holes and electrons. So this is a minority carrier concentration diagram we need to understand for a BJT in active region. So why we are taking the concentration as high as possible in the case of base, because base is a very lightly doped region, and that's why the minority carrier concentration will be high as compared to ammeter and base. Now we need to understand how many currents components are there in the BJT. So this configuration again we are talking about in the active region. So this is in connected this connection. This is uh, ammeter junction and collector junction. Ammeter junction is connected in the forward bias and collector junction is in the reverse bias. So here you can see here ammeter current, base current and collector current. So here the current is flow due to the both charge carrier, that is minority carrier and majority carrier. That's why we call this is a bipolar junction transistor, bipolar, because current is due to the majority and minority carriers, due to the majority and minority carriers. So in the case of PNP transistor, this is a p-type semiconductor, and in p-type semiconductor we have majority carrier as whole and electrons as minority carrier. So this current is representing the ammeter current due to the hole. That's why we represented by P, and this is INE, right? INE, this is ammeter current due to the electron, right? Because electron is minority carrier here. So because this transistor is connected in the active region, so hole is transferred from P to N and again N to P. Suppose if I take 100 holes will be transferred from this ammeter to base. So at the collector terminal we have received only 5 holes. So some holes are recombined in the base region due to the presence of electron here. So 5 electrons are recombined here. If I take some quantitatively analysis, so recombination will be happening in the base section. So you can see here, this is a hole current, this is a electron current, and this is again you can see here, uh, this is in the reverse bias case. So in the reverse bias, there is a concept of reverse saturation current. So in this reverse bias, we have a reverse saturation current as well for the junction of collector to base junction, right? So this is a reverse bias saturation current here. So due to the presence of recombination occurring in the base region, we have a kind of current that is known as base current. So base current, so again you can see here, so if I say reverse saturation current again has two components, due to the hole and due to the electron, right? So generally we have total emitter current due to the hole and due to the electron, again reverse saturation current, because negative sign is taken because by default the current is existing in the this direction, but we have taken assume that ICO is in the direction, that's why we have taken minus sign. This current is due to the electron and this current is due to the hole. So we can say there are four components of current: 1, 2, 3 and 4. These four components are required to understand, and this is a case when, since IE is equal to 0, under operating under open circuit condition, no holes are injected across JE, and hence none can reach JC from the emitter. So clearly, if I say IC is equal to, from this equation we have IC is equal to IC naught minus IPC1, right? IC is equal to IC naught minus IC1, this current, IC naught minus IPC1. If I find the relation between IPC1 and IP, there is a current gain, that is alpha. So IPC1 is represented by alpha IE, and from this equation we have alpha is equal to minus IC upon IE. This is a current gain that is represented by alpha, and this is a generalized equation of collector current as well, right? Next topic is the base width modulation. So base width modulation, as the name suggested, modulation in the width of base, right? Modulation is changing in the width of base, and this effect is known as early effect. And base width modulation is generally happens due to the reverse bias case connected in the collector base junction, that is JC junction. If you connect the JC junction in reverse bias, and in the reverse bias depletion layer, as we know, as you increase the reverse bias in the PN junction, the depletion layer width will increase. So at the PN junction, that is NP junction, this junction, the depletion layer width is increased as you increase the reverse bias at this junction. At some certain limit, this base width, as you can see, previously this is base width is represented by WB. As you increase the JC reverse bias voltage, this width is getting reduced. So you can modify or modulate this base width by changing the value of reverse bias voltage at the junction of collector base junction. This effect is known as early effect. So this is again representation of potential barrier. So you can see, by before applying the reverse bias, it has a base width is represented by WB. As you increase the reverse bias voltage, the effective base width is getting reduced from the physical base width, that is represent WB dash, and this changing in the base width in the base is known as modulation, and this effect is known as early effect. So I think in this lecture I have covered the topic of simple working phenomena of BJT and the base width modulation. So I think these two topics are clear to all of you. And thank you.